should say. So what we need to do is be very, very careful on how we approach and solve these things. We've been talking about these bits and pieces along the way and how you manipulate and use them. Okay, so the very first bit and piece along the way would be, what are we solving for? Okay, so a lot of people will go through and write in atoms, which is phenomenal. That's sort of a unit. Okay, that's really only a partial unit, and I would argue that the partial unit that we've got there is kind of a measurement. Okay, and it's the atoms. Atoms is now our measurement. Okay, what is the substance? Okay, so now the suggestion is that it's atoms of fluorine gas. What is our symbol for fluorine gas? How many elements or atoms are in an atom? One. What did we just write? We just wrote 2 atoms in an atom? That doesn't make sense. That's not atoms of F2. What is that? Okay. Depending on how we want to adjust this, it could be molecules of F2. Is that what I'm solving for? No. Nope. So I don't want molecules of F2. I do want atoms. What would my atom be? Which would be what symbol? F. Just F. Okay. What am I given to start with? 2.25 grams of fluorine gas. Okay, so we're going to make a couple things that we could go through and write here. So number one, we could write to the extreme left grams of our fluorine gas. I'm just going to do that for the moment, and we can drop in the number. Okay. I'm potentially making a big change in how we go through and solve things, so I kind of want your permission. That is how we would initially set this up. Okay. I've noticed that it might be easier for me, maybe for you too, if instead I did this. So now when I start to bring in conversion factors, I build out this way. I build right to left as opposed to left to right. What are your thoughts? No? Fine. It's cool. Perfectly accepted. Okay, the reasoning just has to do with how it aligns. If we go left to right, we don't know how many things we're going to put in there, so we could have a vast white space between the end of our calculation and our equals. Or we could run out of room.
I do like these.
Okay, so it's kind of a mix. It doesn't really hurt one way or another. In this case, we're going to run out of room anyway because there's a lot of conversions that go into it, so it's not going to be a big deal. Okay, so I heard a no to the putting it close to the equals, so we'll go to the extreme left. That's what we've been working with. For future classes, I'll just try and adjust from the very beginning and not go to the far left. Okay, so our grams, we're going to put in that F initially, and like I said, we're going to run out of space, so I'm going to have to cram it in there. 2.25. Does everybody see it at least? Okay. Did I use the correct symbol? Okay. Is G not the symbol for grams?
Yeah, it's the F.
It's the F. What was I given? Fluorine gas. And what do I know about fluorine gas? It's a diatomic molecule, so that anytime I'm referencing fluorine, it needs to be specified as F2, except when? When it specifically says atoms of fluorine. So in this case, that isn't 2.25 grams of F, that's 2.25 grams of F2. Okay? So, is grams of F2 the same thing as atoms of F? No. Everything about what we're starting with makes no sense to what we're ending with. So why should I start with that in the numerator? Okay. It is literally the only given piece of information. That's why we should start with it in the numerator. Okay. I have nothing else to work with from the equation, which means I'm just going to start with that and hope through the process of doing my dimensional analysis it ends at atoms. Okay? So this is kind of a big flip from how we've done things in the past. Because in the past, we picked the thing that we started with that matched our given information or what we wanted at the end. In this case, we have nothing else given. Okay? So Next step. Grams of F2 must get canceled out. What do I ideally want to have appear? Ideally appear. Atoms of F. Okay? So that's what I'm going to suggest you should write. Right? And I saw a lot of people at least attempt this, except they made one really big change. What did they write?
Grams and atoms.
Just grams and atoms. What did I write?
Grams of F2.
Grams of F2 and atoms of F. What's the difference?
No specification.
No specification of the substance. It is going to become incredibly important for you to include the substance whenever you go through and solve. If you start dropping the substance off, you can start ending in false conclusions. Include the substance. Okay? Does the conversion factor exist between grams and atoms? Right? At least not for us. Okay? That means I'm going to have to use some other conversion factor. Right? Could I convert grams to kilograms? Yes. Can I convert grams to pounds? Yeah. Okay? There's probably an unlimited amount of things I can convert grams to. That's why this now becomes challenging. Okay? In the past questions, you were given some other stuff in the question, giving you an idea on where you could go. Here, you're given no other idea. It's now up to you to decide. Right? How do you decide? What was the name of this class?
Chemistry.
Chemistry. And the biggest concept that comes out of chemistry is? Touche. Different letter, different word. Begins with M. Not a bad idea for molecules. Wow, this is getting... I should stop giving you a shovel because I'm getting really buried. Okay. Moles. If you talk to most chemists, they freak out about moles. Oh my God, mole day, blah, blah, moles. Okay, why moles?
They can explain a lot.
Moles allows me to scale up chemistry to a system that allows me to now actually do things with it. So moles are an incredible system, which is why it's kind of you're like, I got no idea what to do. What should you do?
Moles.
Convert to moles.
When in doubt.
Okay? When in doubt, just go to moles. And the reason why is moles are a counting unit. That counting unit can allow me to convert a bunch of different things. I can use chemical formulas. I can use chemical equations. I've got a bunch of different directions I can go. Okay? So that's why it could be helpful. So instead of going from grams into atoms of fluorine, I'll go from grams to moles of fluorine. So now the question is begged, well, how do I do that? Where do I find that conversion factor to be able to do that? Okay. This comes from our molar mass, and that molar mass is found on the periodic table. Fluorine happens to weigh what? 19. How many fluorines are there? 2. 19 times 2? 38. Ultimately, what this is a measure of is the mass. So it's 38 grams. But it's 38 grams in a very particular sample size. What is that sample size? 1 mole of those atoms. We could drop in the 6.022 stuff. 1 mole is a lot easier to write, so let's stick with that. Okay? Notice I already made a mistake in writing that. What was my mistake? I didn't include the substance. This is F2. Okay? Now I can interpret that information into my conversion. What number shows up in front of moles? What number shows up in front of grams? 38. Okay? This tends to flip people out because, well, it's not 1 over 38. Well, this says 38 grams over 1 mole. I can invert that any way I want. Ultimately, by putting it in here, what am I saying to do? Divide by the molar mass. Okay? I don't need to worry about that. The units establish it for me. Okay? What units would I now have? Moles of F2. Okay? What do I want?
Atoms of F.
Atoms of F. Okay? Are those units the same? No. So I need to do something. What needs to happen? Okay, I need to cancel out moles. And in particular, I need to cancel out moles of F2. What do I need? Atoms of F. Does that conversion exist?
Yes.
Not easily. Okay, for those who are saying, well, mole and atom, I've got that. You have mole and atom, true. Avogadro's number absolutely gives you that. And you're converting the measurement of atoms into moles. Are you converting the substance? No. Avogadro's unit or number is a measurement conversion, not a substance conversion. So I can't use Avogadro's number yet. Okay, at least as this is written. Okay? So that conversion doesn't exist. So I need to come up with a new conversion. What conversion do I want to use? Okay? So I heard a suggestion that we should go into molecules of F2. Do you really want to write out molecules every time? No, we could write out just the first three letters. That becomes problematic. Looks like moles. Okay? So that's why I use MLCS. Okay? It's a subtle tweak in it, but enough that it helps me figure out. What is that conversion factor? Well, that's sweet.
6.022 times 10 to the 23rd moles of boiling gas over 1 mole.
So as long as the substance stays constant, I can now align this. Is the substance staying constant? Yes, I'm using Avogadro's number. And I can now insert it. What goes in front of molecules? What goes in front of moles? 1. What happens to our units? Moles of F2 cancel. What am I left with? Molecules of F2. Is that what I want? What has to happen?
Atoms.
I need the molecules of F2 to cancel, and what do I want? Atoms of F. Does that conversion factor exist?
Yeah.
Where does that conversion factor exist?
Yeah, into symbol of F2.
It's the meaning of the chemical formula. That conversion factor comes from a chemical formula. The chemical formula is allowing me to do that substance conversion. There are 2 atoms, 1 molecule. Now I can go through, punch it into the calculator, my units cancel out appropriately, and I've got my calculation. Okay? Those last 2 conversions can actually swap places, believe it or not.
Yeah.
But if we swap those places, the units associated with them change a little bit. Okay? Not a big deal because those relationships will stay constant because we're just referencing the things differently. Okay? There's a couple people potentially balking at that. Should I write that extra calculation out? No. So what's your question?
I did. So you know how you had to take the moles of F2 and then to the atoms of F. I did that and got the same answer instead of going out and spreading it out to 1 molecule is 2 atoms. I didn't.
Sorry, you said 2 moles of F versus 1 mole of F2?
No, how you said we have to stick to the same substance when using Avogadro's number. I didn't do that. I went from 1 mole to atoms of F instead of.
You can't.
But I got the same answer when I did that first.
What has happened is 2 wrongs are making a right, and that's one of the problems that I have with this question, is you can make 2 mistakes in your calculations, and it end up fixing itself. Okay? So a lot of people will go through and say, well, I got the same number. Just because you got the same number doesn't mean you have the same units. And for those people who think it's not that big a deal, it will be a big deal, and it's going to be a big deal in one very important place. On the exam. Okay? You need to track those units very carefully. Okay? So if you think you've got a different process, I'm going to recommend that you talk to me after class and we'll go through and look at it. And likely what happened is you just swapped the order or something just enough where you haven't entirely lost the meaning, but you haven't entirely kept it. And you got lucky in your process. Okay? Potentially being you completely botched your units and you just got lucky placing the numbers. Okay? Which is easily possible. That's one of the kind of spooky things behind this. Right? Is that you can get lucky in the placement of those. Okay? Don't rely on luck for the exam, please. Questions about that? Okay. So in this case, we're converting substances using a chemical formula. Is there another way to convert substances? How do I make water?
Combine hydrogen and oxygen.
What did you just describe to me? If I combine hydrogen and oxygen to make water, what do I have? I have a combination reaction. I have a chemical reaction. That chemical reaction is going to provide a substance conversion. That's literally what a chemical reaction does. It converts one substance into another substance. We can use that as the mathematical expression to solve for substance-substance conversions. Okay? That moves us very cleanly into chapter 9. Okay? It's a chemical equation. That chemical equation is the recipe that allows you to know how much of each of those things need to go through to complete your reaction. The hard part that comes with this is tracking what that how much means. Okay? So, how would you build a bicycle? Just keep it really simple.
Wheels and a base.
You need 2 wheels and a frame. Fantastic. Maybe you even looked at the slides to figure that out. There it is. Okay? Is there a way I could simplify that? Yeah, probably. But you can do better than that. How would I simplify that? Just put a 2 there. Well, that was dumb. That's what chemistry does, literally. Okay? We actually take it a step further, and in chemistry, what do? Okay, that's it. Okay? So when we're looking at a chemical expression or a chemical equation, that's what we're trying to show. Right? Well, why is chemistry so hard? Well, with building a bike, have you seen a bike before? Yeah. How many of you have seen a water molecule? A single water molecule. Okay. If you can't see it, you now have to extrapolate out to this weird nebulous system. That's that hard part. We don't have that tactile response. So we go back to stupid examples like building bicycles to give you some kind of tactile response so that you can try and interpret the equation correctly. Okay? Back to its meaning behind it. That's what we're trying to do in chemistry, is provide that linkage. Some people get it like that. They're like, yeah, it just makes sense to me. Okay? Those people, most people hate. Sorry. Okay? Because they don't get that connection right away. But that's all we're trying to do. Take something that we can't see, scale it up so it's big enough so we can see it, and now what happens when we run reactions? Okay? The other part is the scale up. When you've seen a bicycle, did you see 50 million bicycles? No. Well, to run a chemical reaction, I can't see 50 million bicycles. Okay? To run a chemical reaction, I have to be working with 50 quadrillion bicycles and be able to deal with all of those independent pieces. Okay? So I'm taking something that I can't see, and then I have to scale it up to something that I can understand, and then I have to scale it even further to something that actually makes sense at that level. Of course we get confused behind the scales of those systems. Okay? But that's what we're attempting to work with. That's one of the reasons why we invented moles, is I can't deal with that scale up so big. So what do? I take that scale up and I say, let's just call that a mole. Now it's back down to normal numbers. That's the point of a mole. That's it. Okay? So if we now have simple instructions on how to build a bicycle, someone built 4 bikes. How many wheels and frames were used? So that's always fun. Everyone goes, I can do this. It's 4 wheels. Damn it. This is a conversion question. Most of you are able to do this in your head. As long as you said 4 wheels, that's cool. Don't worry. Acknowledge your weaknesses. You now need the work to set this up. Okay? Most people are like, I don't need to show the work, and they're doing it in their head. For the person that said 4 wheels, great, you now know where your weakness is, show your work. While everybody else is getting it wrong, you'll have your work to prove it right. Okay, so what is the work? How do we do this? Multiply everything by 4? Okay. What am I being asked to do? I want to know how many wheels. I also want to know how many frames. Okay? How many wheels from what? From bikes. What is my conversion factor between bikes? What was I writing? Wheels. One bike, 2 wheels. What is my conversion factor for bikes and frames? Now I can multiply it out and do it. And you're like, oh, that was easy. Dude, that's easy because it's at a scale you can manipulate and see. Okay, you can confirm that with your own internal logic system because you can see the bicycle. You can't see a water molecule. If you're capable to scale the water molecule up to the equivalent of a bicycle, phenomenal, great. You're now having one big step ahead. You can do this one conversion. And now what happens when I string in 3 others? Okay, you still have to have that process to build it. So far, so good? 6 wheels and 3 frames, and how many bikes can be made? That was a little bit longer. Okay, why did it take a little bit longer?
All 3 frames, so it's going back together when you're given what you can have.
Okay. 3 frames makes 3 bikes. 6 wheels makes 3 bikes. It probably took longer because you had, again, those 2 calculations drawn and made sure that those numbers lined up. Okay? We flipped the order. You're still able to process through that. Just 2 wheels, how many bikes can be made?
0.
Oh, this is tricky. We get 1 answer or 0. 1 or 0.
0.
Okay?
You don't.
You're not given any frames. How could you possibly build any bikes if you're only given just 2 wheels? Chemistry does a crap job of this. In chemistry, guess what the answer is? It's 1. Okay, and you go, well, that's dumb. How do we do that? Chemistry is saying, given 2 wheels in your head, in excess of the other one, more than enough, how many bikes can be made? 1. Okay, that is a horrible thing that chemistry does. I do attempt to resolve that when writing questions to make sure it's explicit. Okay, what really should be added here? 2 wheels and plenty of frames. How many bikes can be made? 1. Now everybody should be getting that 1 answer. You're only running 1 conversion here, just the bikes. Make sense? We still okay? Okay. You guys are like, what's the punchline? 3 wheels, 2 frames. How many bikes can be made? Why only 1? I got 2 frames.
You don't have enough wheels.
I don't have enough wheels. What we're introducing with that is a limiting reactant. Okay? Frames limit my ability to build bicycles. Sorry, wheels limit my ability to build bicycles because I don't have enough wheels to completely build out a second bike. Make sense?
Yeah.
Okay? This again gets a little bit weird in chemistry because here we're using a single species, okay, a single tiny amount. If we scale this up to being 1 mole or 3 moles of wheels and 2 moles of frames, now what happens? I make 1.5 moles of bikes. I can't have half a mole. What's a mole? What's a mole?
6 Avogadro number things.
1,000. Can I have half of 1,000? Yes. I can now insert those fractional values into it because the amount of things I'm looking at is so astronomically huge that I'm allowed to get those fractional amounts. Okay? So we have to be a little bit careful with the analogies back to our equations because the equations we're looking at those small numbers. If we scale them up high enough, I can get half of a really large number. I can get 1/3 of a really large number. Okay? Okay. Given 40 grams of wheels, 15 pounds of frames, how many bikes can be made?
What? How many grams?
Whoa. Why the all of a sudden long, like, wait, well, you didn't give me enough information? What does the chemical equation represent? What units? What is the measurement unit? It's a counting. It's a number of them. What is the question asking? A mass. Does the chemical equation or my recipe tell me the mass? No, it only tells me a counting unit behind it. Which means when I hit a question like this where it's now giving me measurement units, I can't use the chemical equation outright. What am I going to have to do? Convert each of those masses into a counting unit. The number of things. Once I know the number of those things, now I can use the chemical equation. Okay? That leap, we're great at right here. You guys all balked at that. That was phenomenal. That was fantastic. I really like that. But if I switch to now to chemistry questions, you all go through and do a conversion straight out of the chemical equation. Okay? The chemical equation only gives you a counting unit. The counting unit that we're used to, or the one that we're going to work with most, is moles. If you're not in units of moles, you can't use the chemical equation. Okay? So, we look at a chemical equation, and this is one of the things that can be a bit daunting on it, so let's take a step back here and breathe. Just clean this up. Read the chemical equation to me. I can call out names if that's easier. 2 what?
2 NO.
What NO? What is NO? It's a gas. It's an atom, molecule. Molecule. When we're used to looking at a chemical equation, it's that single thing. It's that one piece. It's a molecule. So 2 molecules of nitrogen oxide gas
Plus 1 molecule of oxygen gas.
plus 1 molecule of oxygen gas.
Plus
Not plus. It's a reaction arrow now.
with UV light.
A reaction with UV light. Sorry, that one's a bit tricky. I apologize.
Equals 2 molecules of NO2.
Produces 2 molecules of NO2, or nitrogen dioxide. Thank you. Right? That is fantastic. That's what it means. Okay? Well, what if instead of being 2 molecules, I started with 2,000 molecules? Okay? Of the nitrogen monoxide. Well, how many molecules of oxygen would I need to react with it? Why do you know it's 1,000?
2 ratio.
I already forgot what it was. O2? Oof. That's an O. Molecules of O2. I oofed at the O, but didn't oof at any of the other aspects of that. They'll say molecules. Okay, and you said 2-to-1 ratio. Where'd you get the 2 from?
2 molecules.
2 molecules of NO. So when you say 2-to-1, here's what I hear. Is that right? No. So this is where we should stop referencing just random numbers and be like 2 molecules, if we're going to stick with the 2, of NO is 1 molecule of O2. What did you just do? You did a conversion. Okay? And Chloe, because you were the first one to shout out that 1,000, did you do that conversion? Did you write down any of that work? Why not? You could do it in your head. That's fantastic. That's great. Okay? That's okay. What I want you to do is start getting to writing it down. Okay? And the work that we'll go through and show are things that match that you can do in your head so that you start to trust the method. Not because they're always going to be done in your head, but because you trust the method. So that way when the method changes and the numbers change, what happens? You go to the exact same method and you do the exact same thing. And what happens? You get the right answer. It's fantastic. I love it. Right? So we could go through, say, 1,000 molecules of that one, 2,000 molecules of that one. That's great. Okay? If I go into the lab and try and run this experiment, I now need to mix those molecules with each other. Can I measure out 2 molecules of NO? Okay? If I had a multi-trillion-dollar balance that could somehow capture that, yes, I could do that. Okay? Which destroys all science advancements because we don't have the money to be able to pull that off. So that kind of sucks. So all science just stops? No, what do? We scale it up. We scale it up, and instead of running just 2 molecules, I run 2,000 molecules. Can I weigh 2,000 molecules of that? A little bit easier than I could weigh 2 molecules, but it turns out that 2,000 molecules, and now instead of being multi-trillion dollars, it's just $1 trillion. That's not much better. Okay? So I want to scale it up again. Okay? So I continue to scale it up. In this case, I'm going to scale it up to now 12.04 times 10 to the 23rd molecules. That is a lot of molecules. But now I can weigh it. Now I can actually put that on the balance and actually weigh that out. That's cool. Okay? How many molecules of O2 is that going to produce?
6.02.
How'd you do that so dang fast? That was a bit ridiculous.
Not in my head, I just saw it. It was like
In your head, you just saw it. That's cheating. What is our work behind it? Do we want molecules of NO? No. We want molecules of O2. What is that conversion? 2 molecules of NO is 1 molecule of O2. I take 12.04 times 10 to the 23rd and I divide by 2. And the number I get? 6.022 times 10 to the 23rd molecules. Is that any different than if I had picked 2,000 or 1,000 molecules? No, it's the exact same thing. Why is that magic number so important? That is now such a huge number, my human brain can't comprehend it. Okay? Damn. Someone really just say really? Jeez, that was harsh. Phew. Not inviting you to my party. Okay? Let's actually take this a step back. I always make fun of farmers for this, but apologize, farmers. Could have used 24 molecules, 12 molecules and 24, right? My human brain can't comprehend the size of that, so what do? I invent a unit to represent that number. So for the really person, 6.022 times 10 to the 23rd is a hell of a lot higher than a dozen. And we invented the word a dozen to represent 12. Okay? 6.022 times 10 to the 23rd is many factors of magnitude higher than that. Our brain can't comprehend that number so much that we invent a unit to represent it. That unit that we pick, 1 mole. Now everything becomes clean and easy. So when I go back to my chemical equation, where I said it was 2 molecules plus 1 molecule equals 2 molecules, I can now say 2 moles plus 1 mole produces 2 moles. It gets me the exact same system, but it's now up at a scale that I can actually experiment with. That's pretty insanely cool. So our chemical equations are now not single molecules. They're scaled up by a massive factor, and we end up using moles. Because we've scaled it up, do we need to worry about Avogadro's number anymore? No. That's why it's so cool. I used a number that allows me to ignore the number. Does nobody else find that kind of neat? I invented a measurement unit that allows me to ignore the measurement unit. That's kind of cool. That's the point of a mole. That's why people talk about how awesome it is. Okay? But that means when we go into a chemical equation, now our chemical equations are not going to be going through by moles or molecules, they'll be going through by moles. Right? That mole system now makes sense for everything we would use in the lab, which is why everything gets measured out in mole systems or mole relationships instead of molecules. But that also then means that this chemical equation gives me a myriad, just said myriad, thought that was kind of cool, of conversion factors. Okay? That chemical equation tells me, it would be it was balanced. That chemical equation tells me that 1 mole of N2 equals 1 mole of O2. It also tells me that 1 mole of N2 of NO. It also tells me 1 mole of O2 equals 2 moles of NO. How many conversion factors did I just get?
3.
Try again.
6.
6. I get 1 mole of N2 over 1 mole of O2. I also get 1 mole of O2 over 1 mole of N2. Every single one of those equalities generates 2 conversion factors. A single equation, and this is a simple equation, a single equation gets me 6 conversion factors. If we think back to what we did in Unit 1, you had one thing to memorize. Milli meant 10 to the third, which gets you like 1 conversion factor, 2 conversion factors. A chemical equation just drops the hammer and we get a whole bunch more out of it, and that's a simple chemical equation. Right? If we scale this up to a double replacement or a combustion reaction, we get even more conversion factors out of it. This is why it becomes so daunting and challenging to deal with chemical calculations, because you have to recognize that that equation gave you all of those conversion factors. Which one do you use? Do you really want to use all of them? No. You'll probably only use 1. You have to decide on that 1. How are you going to decide on that 1?
Based on what's needed.
Half right, based on what's needed. You're going to decide on which one you use based off of what are you given as a substance and what do you want as a substance. By identifying those 2 key pieces right out of the gate, you can now identify a potential conversion factor that allows you to relate those substances through the chemical equation. Ta-da! So, do it. How many moles of oxygen react with 2.25 moles of nitrogen? So, when we go through to solve this, how many moles of oxygen react with 2.25 moles of nitrogen? Step 1. What do we want? Moles of oxygen. Why is it O2? Because it's diatomic. When would I want it to be just moles of oxygen? Just an O. When it specifically says in the question, moles of oxygen atoms, does it ask for atoms? No, so it's O2. Okay, that's the issue with our diatomics. What were we given to start with? I'm going to balk at the 2.25. We were given moles of nitrogen. How many moles? Now our 2.25. Okay. Is moles of nitrogen the same thing as moles of oxygen? No, so we set up a conversion. Moles of nitrogen, and ideally I want moles of oxygen. What am I converting in this conversion? What am I changing? It's the substance. Where do I find a substance conversion? In a chemical equation. I did make one subtle change to the question, and we're going to evaluate that in just a second. Okay? But in this case, it's not going to affect it. Where do we get those numbers? It's the coefficient in front of each of those species. So remember when we had to balance equations and I asked what's the sum of the coefficients? And it was really important to know that number so that you could answer that question. It's also really important so you can write numbers in your conversion factor. What are those coefficients? 1 and 1. Now what happens? Moles of nitrogen cancel, and we'd be left with moles of oxygen. Is that what I want for an answer? Yeah. Yep, so 2.25 times a resounding 1, and I get 2.25 moles of oxygen. Should we change the question? A little bit. Let's a little bit change the question. So we're going to keep the moles of nitrogen, except I'm going to make this the moles of
NO.
nitrogen oxide. Okay, because we worked through that first one, let's kind of talk through this one together. Do I want moles of nitrogen? No. So that needs to show up in the denominator. Moles of nitrogen. What needs to show up in the numerator? Moles of NO. What do I do? What's it's 1? I don't know what that means. 1 mole of NO is 1 mole of N2. Where'd you get that 1 from? The coefficient from what? From the chemical equation. Say that again.
You have to know about balancing out equations.
Is that chemical equation balanced?
No.
No. So you're using coefficients that don't make any sense because the equation is not balanced. This would be like saying to build a bicycle, you just take a wheel and a frame. That's not a bicycle. At best, that's a unicycle. Okay? That's not a bicycle. I need 2 wheels in one frame. You have to make sure the equation you're working with is balanced, which means unit 2, back it up, balance your equation. Oxygen, 2. Go back and check our work, and we notice that the number in front of NO is 2. Our answer is not 2.25, it is 4.5. 2.25 times the 2. Okay? For those of you that may have been paying attention really subtly, if we take a look at the NO, magic. I had erased that 2 earlier to make sure that we could have this discussion. When we're looking at our conversion factors between substances, we have to make sure that that conversion that we're looking at is valid. It has to be a balanced chemical equation. Okay? Yeah, that's a bunch of stuff. So, equation concept and the strengths. How many moles of CO2 are necessary to make 1 mole of sodium hydrogen carbonate? Oh, God. Yeah, do it. There we go. I like that sound. You just click. Whoops. Moles of sodium hydrogen carbonate, the same thing as moles of CO2? No, what do I need? I need a conversion. I heard you, Kelsey. Give me a second. I'm guessing I know where that 2 is in just a second. What 2 are you referencing?
I was looking, like, if you had to, like, balance it out first, the 2 in front of the edge.
Okay. This conversion factor comes from, what are we converting? What's the thing that's changing in that box?
Sodium hydrogen carbonate.
Okay, so we could directly reference it. Sodium hydrogen carbonate is becoming CO2. What is sodium hydrogen carbonate? What is CO2? A substance. Okay? How do we convert substances? Using a balanced chemical equation. So we go back to our chemical equation, and we would pull the coefficients from our balanced chemical equation. Okay? Interesting, there's only one coefficient shown, which is, I think, what you're asking about, Kelsey.
Yeah.
Is this 2. Are there coefficients in front of all the other ones?
No. Well, there's a 1.
There's a 1, so there are coefficients there. So why is that 2 there? How many sodiums are on the left-hand side? 2. How many sodiums do I need on the right-hand side? 2. Why is the 2 there? To balance the chemical equation. If you go through and check all the work here, I actually balanced it for you. That's why the 2's there. Okay? Always a good idea to check and verify that. Okay? But if you see numbers there, it's probably because the equation was balanced for you. Okay? So since the equation is balanced force, now all we have to do is pull the number straight out of the equation. What is the number in front of CO2? 1. What is the number in front of the other one? 2. What's our answer? Half a mole. I can't have half a bicycle. I can have half of a mole. Remember, a mole is a massive number. I can have half of 1,000. Okay? I can have half of 100. That is allowed to happen. Okay? How many moles of sodium hydrogen carbonate are produced when 1 mole of sodium carbonate, water, and carbon dioxide mix? Said another way, I'm taking 1 mole of sodium carbonate with 1 mole of water and 1 mole of carbon dioxide. What do I have to do? Okay, I'm hearing the phrasing out there. Yes, I have to set up 3 conversions. Okay, so at least one person is on board with that. Should I write out those 3 conversions? I'm hearing a no, so we're going to settle through that. For those of you that are questioning that, write out those 3 conversions and show me after class. Okay, the answer you'll get, before we do that, the answer we'll get for that is 2 moles of sodium hydrogen carbonate. Okay? What is the mass in grams of sodium hydrogen carbonate produced when 2 moles of CO2 are consumed? How many think that's a straightforward question? One conversion. No. Okay? Set it up. See what can you put down. Okay? Get through as much of it as you can. Identify the things that you need to eventually go through and do. If you get stuck, raise your hand. I'll come to you. Talk to the people around you. See what you can come up with.
Grams of NaHH2.
What are we starting with?
Moles of carbon dioxide.
Okay, do we have a number of moles of CO2? Yes. So now here's where our units really come in handy. Remember when we talked about units, we said there were 2 pieces. What are those 2 pieces? The measurement and the substance. So I can compare across. There's the measurement, moles, there's the substance. I look at my answer, what do I have? Close I do. I have the measurement and I have, pick blue, and the substance. Did the measurement change? Moles to grams. Yes, I have to do some kind of conversion there. Did the substance change?
Yes.
Yes, I have to do some kind of conversion there. Okay? Those conversions cannot happen at the same time. Substance-substance conversions happen independent of measurement conversions. Okay? We don't combine them. Right? So now the question becomes, well, which one is important? Which one should I do first? Okay? If you don't know, start referencing through them. Moles to grams. Where do I find a relationship between moles and grams?
The periodic table.
Periodic table. Okay, straightforward, straight out of the periodic table. Great, it gets me grams and moles. Fantastic. For how many substances? 1 substance. If I say 12 grams of carbon, how many moles? 1 mole of carbon. Okay? That's what the periodic table tells me. It tells me for that single substance. Okay? Let's take a look at our substance. CO2 to sodium hydrogen carbonate. Where's that substance conversion found? From a balanced chemical equation. What if this was all you were given?
You can add the bonus. You can
You need that equation. Literally, you have to have that chemical equation. If you don't know how the substances convert, you cannot do that conversion. It does not exist. Okay, why? There are multiple ways that I could get CO2 and sodium hydrogen carbonate to interact with each other, to somehow come through a chemical equation. I have to know which of those very specific chemical equations we're using to do that conversion. Okay? I have to know that chemical equation. Don't erase that part. Okay? So I now have that chemical equation, which gives me that information. It gives me a conversion factor. It allows me to convert the substance. But hold up, a unit is two things, a measurement and a substance. While the chemical equation does give me the substance, it must also give me the measurement unit at the same time. What is the measurement unit tied to my chemical equation? Coefficient is a number, not a measurement. It's moles. Okay? So I am allowed to use a conversion factor from the chemical equation as long as I am in what units? Moles. What do I start in? Moles. Should I convert to grams first? No, why not? Because then I can't convert the substance. It becomes literally impossible for me to go through and solve it. Okay? So the first thing I'm going to go through and do is that mole conversion. Why am I placing moles of CO2 in the denominator? To cancel out. What do I want in the numerator? Sodium hydrogen carbonate. Why did I not put grams of sodium hydrogen carbonate? Okay. So at this stage we're saying we aren't doing that. We just talked through all that. Mike, why would we do that? Can I find the relationship between grams and moles? Yes. Where is it found? On the periodic table. Can I find the relationship between the grams of sodium hydrogen carbonate and the moles of CO2 on the periodic table? No, the substance changes. The periodic table only gives me one substance. Where do I find that conversion factor? Balanced chemical equation. And it tells me 2 moles of NaHCO3, 1 mole of CO2. This conversion comes from that balanced chemical equation. Okay? What unit would I now have? Moles of sodium hydrogen carbonate. Is that what I want for an answer? No. So moles of sodium hydrogen carbonate needs to be in the denominator so that it cancels. What shows up in the numerator?
Grams of sodium hydrogen carbonate.
Grams of the sodium hydrogen carbonate. Where is that found?
Periodic table.
Periodic table, where we just add them all up. So 23, 24, 36. What was it?
83.92.
Did somebody else get that?
84.01.
84.01.
Okay. There was enough of a chorus saying you're wrong. Sorry. So we're going to go with 84. Yeah. Oh, you said 83.92?
Yeah.
There might be some weird rounding thing going on there.
Well, she's got a table with different values.
Oh, okay. I'll address that in a second too. Okay. The moles of sodium hydrogen carbonate cancel. What unit would we now have? Grams of sodium hydrogen carbonate, which is our answer. Now we can enter in the calculator and we get our lovely answer. Okay. The units allowed us to solve this. If we swapped the order of these, what we would notice when we went through to solve, because we said, just for those of you that are like, well, Mike, you're just full of crap. We could have switched this around. We could have done moles and grams, and I could have done this 84 there. You're right. But what were we converting when we did that grams and moles? To CO2. Which then, when we try and go through and do the next conversion to get rid of CO2 and bring in sodium hydrogen carbonate, this would be moles. This would be moles. The units don't cancel. Okay? So this is why we follow the unit system through this to track it very, very carefully. Okay? So with that, we are done.